Okay, this is a thermostat, basically for a heat pump system. Notice here on this heat pump thermostat, we have an off, have a cool position, have a heating position, and emergency heat. On all heat pump thermostats, whether they be mechanical or digital, they have a function switch that the homeowner can switch to emergency heat in the event that in the event that the heat pump does not operate correctly in its normal mode. Now here we have an interesting, this looks like the, oh, okay, I know what this is. This is a four-way valve. And I believe this is the installation of a four-way valve utilizing a wrapped blanket. Heat absorption technology. See if I can find it in your textbook. I believe that's on page 1279, figure 43.10. Shows a wet rag wrapped around, and basically it is designed to absorb heat while brazing this in. This is a very difficult operation. If you're a novice, you don't have a lot of experience installing this type of stuff, it's very good idea to learn the process. It can be done, but it takes a lot of diligence. It takes a lot of heat protection. These four-way valves are very heat sensitive. If you don't do it right, the brand new valve that you install will probably get stuck and quit working. Okay, here's an air handler. Notice down here we have, probably in this section here, we're going to have the basically it's divided into two areas, one for the blower and one for the evaporator coil. And then you have provisions made inside this air handler cabinet so that you can install the strip heat package that you'll need, or emergency heat as needed. Most of these cabinets are operated at 230 volts. They're typically not normally 115 volts. I haven't yet seen a 115 volt version of this. And also you have to run two circuits. Typically you're going to run one just for the heat pump operation, and then the auxiliary strip heat requires a separate circuit and bigger wire sizing in order to power up the heating packages that are installed. Okay, here's a Carrier package heat pump system. And of course, all your components are located in here. You have your ductwork that connects up either side by side or bottom discharge on a roof curb. Scroll compressor, which is designed for heat pump application. They're beefier. They take a lot. They're designed specifically for heat pumps because of the high coefficient of performance factor that is involved. Please remember, when you are changing a compressor on a heat pump, I don't care what brand it is, you need to make sure that the compressor you're installing is rated for heat pump duty. There's a big difference between a heat pump compressor and a standard air conditioning compressor. Okay, this is a dated video, basically showing an old, I actually installed thermostats like this about 15 years ago. This is an earlier version of a digital thermostat. This one here was a battery-free one. And basically this would give you the different features of this. The modern day versions are usually a full screen. They're much bigger. These thermostats, when I put them in, were state of the art at the time. But I can tell you I've taken out most of the ones that I put in 20 years ago because technology has passed them by and they started having problems with these. Okay, here we have the check valves, basically on the cooling to the indoor coil. So basically, if we have refrigerant going from the outdoor coil, notice that it bypasses this one valve, goes directly through this check valve to the indoor coil. Now we go from the indoor coil, and notice we bypass this check valve, and then we go to the outdoor coil. One thing I got to call your attention to, Carrier Corporation and some other manufacturers do incorporate these check valves in their coil designs, and you need to be aware that you could have problems with these. I've seen these check valves stick for whatever reason. Don't ask me why, but they do stick and they do cause problems. Okay, here we have the basically showing a heat pump system. This was covered in the previous PowerPoint lecture. And notice that we're utilizing a capillary tube as our metering device. Notice that we have a filter dryer and a check valve for each metering device. So basically our metering device consists of a capillary tube and the check valves. And then notice that we have filter dryers for each segment. Typically, you're only going to find one filter dryer for the whole thing in the new systems. This was just one type of system that was manufactured years ago. And notice on the compressor, we have the common port right here through the bottom. This never changes. The thing it basically changes is the position of this slider right here. That changing position is going to indicate what mode of operation this thing is going to be in. We explained this earlier in the PowerPoint presentation, but just be aware, this is a standard design. There are specifics that come along with it. Okay, here we have a diagram basically showing the refrigerant flow on the indoor unit. Obviously, in this mode here, the previous one was cooling. This one here is heating. Why do I say that? Look at the gas line. It is coated in red. Notice that the filter dryer is, look at the direction of the flow of the refrigerant here. So basically, this filter dryer, of course, we're utilizing this in heat mode. And of course, we are radiating heat and taking heat out of the outside air and bringing it inside. And once again, the compressor connection here stays the same down here, but look what happened here. This slid over. Okay, so what's going on here? Is this thing either heating, cooling, or not doing anything? Good question. So in this particular position, let's see if I can find the diagram, make sure that I have the correct information I'm giving you guys here. Okay, in this diagram here, which I think is found on page 1285 of your textbook, basically, we are, this is figure 43.21, placing a liquid line filter dryer in the heat pump refrigerant piping. So basically, here's your filter dryers for the cooling side and for the heating side. And remember, typically on most heat pump installations, split systems I'm talking about now, they're typically going to install a biflow version of this liquid line filter dryer. Now we're talking about the pistons. This is found on page 1284, figure 43.19. This piston basically acts as, if I'm not mistaken, is this the one that has the check valve in it? So when the flow is reversed, yeah. And then basically this serves two purposes. It restricts the flow of refrigerant from high pressure or low pressure, and it also acts as a check valve. Now, These things are different from the indoor coil to the outdoor coil. Please remember, you're typically going to have two metering devices, and if they have this check valve design feature, do not interchange the indoor with the outdoor piston. They are very specific. So if we have the flow of refrigerant, in this case hot gas, going through here, notice that the piston is allowing for the full flow in this position. Now in the metering position, we're blocking off the flow of refrigerant and we are metering. So this thing is a dual function piston. We can use it as a check valve in one position and as a metering device in the other. These are very common out there. In this particular illustration, which is also found on 1285, look at the this one here utilizes a capillary tube for that's interesting. It uses a capillary tube for the indoor cycle and a TXV for the outdoor cycle. So that's kind of interesting. So we have two metering devices, one for the outdoor section, one for the indoor. So a cooling capillary tube for the cooling cycle. Then for the heating, they're utilizing a TXV. I honestly have never seen one of these. Okay, in this illustration here, we showed the check valve and in this position, and we saw the check valve in this position here. So at this point, we are not moving any refrigerant. So I'm going to have to, let's see, based on what I see here, this is just basically showing the flow of refrigerant and how the units are connected together. Okay, so why is it important to look at the brazing techniques here? We all know how to braze, correct? Probably not. So what are they talking about, Larry? Well, what they're talking about here, there's a right way and a wrong way to braze connections. There's such a thing as putting too much brazing filler material in when you are doing this. And if you do not do it correctly, you are going to have problems. Simple as that. You will have problems. So it's very important that you pay attention, that you, when you take these fittings apart, such as like on the, if you're taking a reversing valve out, you need to remove this extra filler material on the old pipe stub before you braze in your new reversing valve, as an example. You don't clean this off, you're going to have a hard time with the new one. If you don't clean these parts off, you're going to have problems with connecting this stuff up. Do not assume you can just heat this up and put it right back in again. Sometimes it works, sometimes it doesn't. Okay, basically here we have the operation of what a heat pump does in the heating. Notice that this is in the heat mode. The outdoor air temperature is 0 degrees. The return air is 70 degrees. We covered this slide previously in the PowerPoint. Now notice that this thing here is in the air conditioning mode. Now this functions as a normal air conditioner. Notice that design ambient outside is 95. Design inlet return air is 75 degrees. Of course, evaporator coil is located here. Return is 75, and we're coming out with 55. So if you look at 75 minus 55, that equals 20 degrees delta T, which is probably the correct temperature difference for this application. Okay, now we have something rather interesting here. I am not sure. It says warm air out contains heat from ice cream. So basically, this is a refrigerator, obviously. Basically, we are extracting any heat that's inside this zero box and through the evaporator coil. And then, of course, we're rejecting the heat through the condenser. And, of course, the air leaving this condensing unit on top of this refrigerator is in the form of warm air from the heat that was absorbed from the ice cream. The idea being, it doesn't matter what kind of a product or building, everything contains heat, including ice cream. If you want the ice cream to be nice and solid, you want to make sure that you are pulling the heat out of the ice cream. Otherwise, it's going to be soft. Okay. Okay, here's an R410A system. Notice that we have, this is in a heating mode. Okay, we have 35 degrees coming into the outdoor coil here. The coil temperature is about 10 degrees. We're going to start forming frost at this point. Our low side connection here is going to be 62 psig. The suction pressure, 62 psig, corresponds to a refrigerant boiling temperature of -10 degrees for R410A. So you got your suction line, liquid line, and of course you got your return air. And then of course we are putting heat through the supply air connection. Remember, we're absorbing heat from the outdoor coil and rejecting that heat in the indoor coil. We have 3 positions that you'll encounter when you're installing split system heat pumps. One of the more common positions that I would say you'll find some upflow out there, a lot of horizontal. The job I did in Port Orchard, Washington this year was a downflow. This is not very typical. This is a little bit more challenging, required some different things on my part in order to make this installation successful, but I have pictures of it and hopefully I'll get a chance to share those with you in the classroom. A downflow heat pump system replaced this was a propane downflow furnace, and the person that I was doing this job for did not like paying the very high price of propane that he had to fill out in this large tank out, just out away from his house in Port Orchard. And so he elected to go with a ream heat pump system, which was a good decision on his part. We're bringing in return air from the there was originally a return air in the hallway. Then I put in another return in the living room in order to increase the airflow requirements. And his house had what they call a perimeter ducting system, very generous crawl space underneath the house. In fact, it's one of the few houses that I will tell you that I actually like working underneath the house. I could actually sit up and in some places walk underneath the structure of this house at Port Orchard. Very well designed. It was not a major mess like most of the raised foundation houses I've encountered here in California. There's a ducted version of the I should say a package type heat pump. We talked about this earlier. Okay, we talked about this diagram about the first stage of cooling. Remember, you energize the 4-way valve. Here we have a diagram showing the thermostat components on a heat pump stack. This looks complicated, but it's not. I want to call your attention to a couple things. You have 2-stage heating and 2-stage cooling, plus you have an emergency heat position. These represent the various switch actions that the customer can engage, whether it's a manual rocker type switch or a digital switch. And notice that you have different components. The E terminal on this subbase is going to energize the emergency heat relay. Y is going to energize the cool relay. X is basically indicator light. And what this does, when you energize the emergency heat, you're also going to energize the X terminal, which in turn is going to bring on the emergency heat light, telling the customer, hey, the emergency heat is on. Please pay attention to that. If you have auxiliary heat on, same scenario. It's going to bring the, this light will come on as well, depending on the manufacturer. But this one actually is designed for the emergency heat only. But I have seen the auxiliary heat having a red indicator light to let the customer know. Then of course you got the R terminal, the G terminal for the blower. And now in this particular case, we're utilizing O as the terminal for the changeover relay. On some thermostats for heat pumps, it's going to be the B terminal. And when you take and install one of these, especially on the electronic thermostats, you have to select either O or B. Which time, when is it energized and or not energized, depending on the heat or cool. And the manufacturers are not all uniform on this, I might add. So I want to make sure you understand that. Okay, here's another diagram. In this case, we're showing the cooling position. So this would be the diagram showing what is taking place. Notice that the fan switch is in the auto position here. Okay, so auto position, and of course you got your cooling taking place here. Emergency heat is off, got our power. Now, interestingly enough, I don't see the common terminal shown here. Most thermostats today, in order to get rid of the battery, require a common terminal. Okay, I do not see it here in this diagram. And in this case, the O terminal indicates a changeover relay. Okay, here in this particular, this is the emergency heat mode. The compressor stops. The W terminal controls all electric heat. So in this application, even though these are calling, basically what happens is we're going to emergency heat because the switch has been activated, contacts are closed. And remember, in this particular case, this will bring on the strip heat in the blower cabinet. Second stage of heat here. Remember, you got a first stage, which energizes the four-way valve. The second stage energizes the compressor contactor. First stage of heat simplified here. First stage, you're going to just energize the, in this case, we are going to, we're going to either energize or leave the terminal open, depending on the manufacturer. So once again, just remember when you are checking out the wiring schematics on these heat pumps, it's really important you know what the manufacturer is calling for as far as energizing, de-energizing. If you do not understand this, you are going to have some issues with this. These diagrams, by the way, can be found on pages 1294, 1295. Basically on this one here, first stage of heat, this is figure 43.39 on page 1294. And basically the temperature drops below the cooling set point, first stage of heating, pressure starts, the time the four-way magnetic valve is de-energized and the unit will be in the heating mode. So in this particular application, we're not going to energize the reversing valve. Second stage of cooling. Take a look at that. Okay, second stage of cooling. This is also found in 1294. It'll show what happens in a rise in temperature. The first stage of thermostat's already closed. The second stage closes and starts compressor. Compressor was the last and will be the first off. We covered this in the PowerPoint previously. Okay, this is a chart just basically showing the suction pressure at the service valve in the heating mode and in the cooling mode. So basically this chart, I believe, is in your textbook. I know I saw it here somewhere. And I believe this is on page 1309, figure 43.57. Shows a performance chart for a 36,000 R410A heat pump system. Okay, here we have the just a simplified schematic diagram showing a thermostat, 24-volt power supply, the path of conductor, and the magnetic holding coil. So this would be just a very simplified circuit showing how this circuit is energized. Basic electricity. Very, very basic. Keep it simple. Only equipment that was manufactured. By the way, this diagram is found on page 1304, figure 43.54. It's a basic example of a power supply, a path or conductor, and a load for consuming power. Remember, all circuits consist of loads and switches. That's it. Just loads and switches, nothing else. Okay, we discussed this in the PowerPoint presentation earlier. This is another diagram. Now look what's interesting. Here we have a situation in this diagram of this schematic, and notice that we show something that is stuck closed. Now, what is going on between terminals 3 and 1 stuck closed? Could that happen? Sure. Does it happen? Sure. So what is it? Well, let's find out. Let's see what the book has to say about that. Okay, on page, would be page 1316. This is going to be found under figure 43.63. Excuse me. The contacts that change the unit to cooling for defrost are stuck closed. So if this happens, you're going to have problems with the heat pump. Does this happen? Yep, sure does. Okay, now here's a temporary jumper applied to this diagram over here. So what's going on with this temporary jumper over here? What is going on with this temporary jumper? When all else fails, install a temporary jumper. By the way, this is under service calls under air source heat pumps on page 1315. In this application, when the unit's off, the technician applies a jumper wire from terminal 3 to 4 to cause the a defrost, to avoid having to wait for the timer. Because this is a high voltage circuit, this exercise should not be performed unless the technician is very experienced. So what we're doing here is we're testing the defrost portion of this heat pump by manually overriding the timer here with this jumper. Needless to say, extreme care needs to be taken care of when you are bypassing with a jumper wire to make sure that you do this so that you can initiate the defrost. Typically on the modern defrost boards, it's on the low voltage side now, but there was a time when you had to do it on the high voltage side. This is the scroll compressor showing how refrigerant is compressed. This is how the refrigerant is on a fixed and orbiting, the fixed scroll and the orbiting scroll. Notice that the high pressure goes out through the center port, low pressure goes in through the side port. So refrigerant going in as a low pressure, low temperature vapor, leaving as a high temperature, high pressure vapor. And then of course you got the air handler here. You have the return air duct, you got the fan, and of course you got the large suction line, the liquid line. And basically this is going to, I want to check and see what the book has to say about this. This would be the indoor section. Oh, I see what's going on. Notice where the heating elements are mounted. Heating elements are located below the indoor coil, okay? So in this case, the strip heat package is located below the indoor coil. That's very important because if you install it where you think it might work the best, you're going to have problems with it. This you're going to find on page 1310 under 43.58. The heating coils are below the heat pump coil will cause a very high head pressure if used incorrectly with the heat pump. So where these things are located have to be where the factory says they should go. If they're installed incorrectly, you will have high head pressure problems to deal with. Okay, this is the total heat of rejection, the net refrigeration effect, and the heat of compression on a heat pump. And heat pumps, in their very nature, are a very efficient machine when they're designed properly, installed properly, and charged properly. That being said, if you take some shortcuts and don't do the job right, you are going to have problems with this system. I can tell you I've had a lot of experience installing heat pumps over the years, and for the most part, I've gotten very good service life, typically in anywhere from 12 to 20 years of continuous operation. And this is basically in the state of Arizona, by the way, I might add. I've done a lot of work over there in the past, and they work extremely well. Okay, here we have a situation where we have the second stage of heat with outdoor stat. So basically what we're doing is we reach the balance point of this heating portion of the heat pump. In other words, the heat pump can't keep up with the cold air infiltration of the structure, we may have to energize the auxiliary heat contactor. And notice that each one of these strips has a sequencer. Basically, they don't both energize at the same time. Typically, you're going to energize the relay, and then we have a sequencer which will energize one stage of strip heat, and then later on it'll energize another stage of strip heat. And then we have an outdoor thermostat, which is going to allow which stages to come on in this case. So we have an outdoor thermostat that's going to have a sensor which will determine, in this case, at 30 degrees, we'll energize stage 1. At 20 degrees outdoor temperature, we energize stage 2. Okay, we talked about this earlier in the previous PowerPoint presentation. Airflow is extremely critical on a heat pump. If the ducting is not done correctly, you're going to have the cold side effect. You will have areas that will be too hot, areas that are too cold. Heating, this is a critical issue. So pay attention to the ducting design when you're installing a heat pump, whether it be a split system or a package unit. And we've talked about that. This ducting is done correctly because the return's in the center. Supply ducts, in this case, is perimeter, outside walls. You want to cancel out that cold air. Outside walls, this is done correctly. Return in the center, supply towards the outside, and this works extremely well. Now the problem is, well, Larry, how do you install this ductwork way over here at the bottom of the roof line? Well, when the house is being built, that's easy. When you are trying to retrofit a 100-year-old house, well, good luck. It shows the of the removal, heating up. In fact, you'll find this on page 1279 of your textbook under figure 43.11. The valve and stubs are being held in a vise while additional stubs are being brazed in. Remember, valve body must be kept cool during the process. The valve and stubs can be installed in the unit by cutting the stubs off. They recommend, in this case, that you braze on stubs in a prior to installing a replacement reversing valve. That may or may not work. I personally would rather install a reversing valve as it comes from the manufacturer to the existing piping arrangement inside the heat pump. It's harder, but the thing is, if you protect that reversing four-way valve, you should not have any problems. But the critical issue here is putting a heat sink here to prevent that heat from the torch from affecting the internal Teflon seals and all the things that are inside of this four-way reversing valve. Very critical issue. This is what a four-way reversing valve looks like from the manufacturer. Had an interesting situation in Temecula a couple weeks ago. This little capillary line right here developed a leak. I've never seen that before. And the leak was so significant that this heat pump would not operate anymore. Of course, it was out of refrigerant. And I had to use my ultrasonic leak detector. I found the leak in this pilot line right here next to the solenoid. And I was able to successfully clean this up, heat it up, and braze the and repair the leak and make this reversing valve workable again. And by the way, this unit had like 5 or 6 pounds of R22. In case you haven't priced out R22 lately, it's through the roof, if you know what I mean by that, as far as cost goes, because it's no longer manufactured. Okay, this appears to be a defrost board. You will see this a lot in the current heat pump designs that are out there on split systems as well as package units. I find the boards not to be very intimidating. They're very easy to troubleshoot. What I like about these boards, you will find this on page 43, page 1301, figure 43.48. And basically, this is just a solid state board, a defrost board that you'll see on the current technology. And you do have a provision. They usually have pins right here. I believe these are your shorting pins in order to energize the defrost with a engineering bypass wire. We don't call that a jumper, by the way. in order to bypass the electronic timer to test the defrost action of this thing. Okay, here we have a sensor, and notice the coil design here. This is what I call the hairbrush, the very hard to clean type of coil. This one here is a thermistor used to sense the temperature of the outdoor coil. I suspect that particular manufacturer is Train Corporation. They, for many years, have manufactured aluminum outdoor units utilizing the aluminum spline technology. My gripe against that type of technology, those things are very hard to clean. Very, very hard to clean. So if you have a unit that is not functioning correctly, it is of this design. I will tell you there are a limited number of options that you can do to clean these things. I would stay away from using harsh chemicals because aluminum will corrode, and you need to take and keep these things clean. But this is the thermistor operating the defrost. Okay, this is it's not a tuning fork. This is actually a special type of welding tip. Basically, you would hook it up to your oxyacetylene torch handle, and basically you would have a flame which comes out of this side, a flame that comes out of this side. Now, in theory, if you use this fork heating mechanism, it applies heat evenly across the joint, but it takes special practice to operate and utilize this tuning fork torch tip. I do not personally use these in my business. I find that they're more of a hassle than they're worth, but this is one method that you can utilize when you are installing reversing valves to apply heat evenly. Okay, here's the reversing valve. Notice that he's using the tuning fork concept. So in theory, if he does this correctly, he's going to heat this up. Now, the one thing I see wrong with this picture, it's pretty obvious. Do you see any form of heat protection taking place up here? I certainly don't. I think they're just demonstrating the uses. The other thing which this slide does not indicate, you need to run nitrogen through this thing around 5 psi. We do not want the oxygen oxidizing inside of this reversing valve, especially with 410A and POE oil circulating in this system. The POE, in conjunction with the 410A refrigerant, will cause that oxidation to break loose, and you could actually mess up the interior surfaces of this reversing valve. Okay, we talked about this in the PowerPoint presentation. This thing here is the mechanism that's going to slide over from heating to cooling. So for cooling, notice here, you're going to see this app, and I believe, just for your information, it is in your textbook. Talked about it this morning, but we'll talk about it again. This is extremely important if you do not understand the four-way valve process. Okay, this particular one is located on page 1276 under figure 43.5. So the internal slide of the four-way reversing valve solenoid determines the position of the slide. Most systems operate in the heating mode when the solenoid is de-energized. Position of the slide when the solenoid is de-energized. B is going to be the position of the slide when the solenoid is energized. So de-energized, energized, okay? Okay, another wiring diagram. Notice that you got heat anticipators. Notice that you got your terminals here. The E terminal is, of course, the emergency heat relay. Y is your cooling relay. X is going to energize the emergency heat pilot light. And of course, your W2 is going to be hooked up to your auxiliary heat relay, which will bring on your electric strip heat. Your transformer, interestingly enough, I do not see the common side. So this is kind of incomplete because normally you have a common connection at the new digital thermostats in order to eliminate the battery use. Then, of course, you have the blower relay, changeover relay. Okay, in this position here, the top one shows what happens when this thing is running in the heating mode. Notice that the compressor is still going to run. Notice that the heat pumps always usually have an accumulator. The idea behind the accumulator is to catch any liquid refrigerant because we do not want this liquid refrigerant entering the compressor. Got that? We do not want the liquid refrigerant entering the low side of this compressor. We have an accumulator to protect the compressor from liquid refrigerant. Notice that the discharge line, in this case, is always common to the single port on this reversing valve. Heating mode, obviously the valve slider has changed positions. Notice that we still have the discharge going into the four-way valve. And of course, we still have the accumulator. In this case here, we are putting in cool air through the indoor coil. And of course, we're rejecting heat from the indoor coil through the refrigerant to the outside. Okay, another picture showing what happens when how it electrically looks in the heat mode. This is the slide switch energized to heating. Notice you got your anticipators. Notice that we have as the temperature falls, heat 1 will come on. As the temperature continues to fall, then the second stage will come on. The anticipators are designed basically to prevent overshooting of the thermostat. Today it's done electronically. And they're very accurate within 1 or 2 degrees. I've never had no issues. Okay, this shows what happens with the refrigerant in winter and summer. In the winter, you have hot gas going through the large suction line, warm liquid, not hot liquid, going through the liquid line to the outdoor unit. In the summer, we have cold gas going through the suction line back to the compressor. And we have warm liquid leaving the outdoor condensing unit coil, outdoor unit, going to the metering device. Remember, on heat pumps, you usually have 2 metering devices, one for heating, one for cooling. Summer operation, refrigerant line, large one is going to be cold gas. Small refrigerant line is going to be warm liquid, direction of flow, indoors to out, and outdoors to in. In the winter operation, it's just the opposite. The large refrigerant line now becomes hot gas. The small refrigerant line becomes warm liquid, outdoors to indoors, and indoors to outdoors direction of flow. And just bear in mind that if you don't have 2 ports necessarily on the outdoor heat pump section, you actually have a 3rd port so that you can check the pressures correctly in the heating mode as well as the cooling mode. If you do not put your gauge manifold hoses on the right access ports, you'll actually peg out one of them during the heating mode. There is a 3rd connection. I don't know if the slides here will show that 3rd connection. So you can actually look at the pressure temperature relationship in the heating mode as well as in the cooling mode. Okay, this is a thermostat up here. We're utilizing the O terminal. And notice here, we're in the heat mode. Emergency heat, in this case, is energized because the slide switch is energized. In this case, the emergency heat relay has energized the strip heat. The auxiliary heat package consists of 1 or 2 or 3 elements. Don't forget the heating elements have sequencers to prevent them from all coming on at the same time. We talked about this earlier, about the outdoor thermostat in conjunction with the timer in order to energize defrost. And typically the timer is designed to close for 10 seconds every 90 minutes of operation. And if this thermostat does not close, defrost will not come on. Simple as that. Okay, we talked about this morning in the PowerPoint presentation. Of course, this is your outdoor unit. This is your horizontal indoor unit. You got your return air, you got your supply air, condensate pan. This looks like a normal installation of a split system gas heat and air conditioning system, except in this case, you don't see a flue pipe, number 1. That's gone. You don't have no gas connection, number 2. In this case, we are reversing the flow of refrigerant in order to supply heat to the house inside. Okay, this is utilizing an ohmmeter to check the 4-way valve solenoid coil. Notice when we have this the ohmmeter or the if we have our meter in the ohms position between the 2-watt coil wire connections, we have 20 ohms. This indicates that we have a good winding on this solenoid coil. Now, if you take a look at the second picture, look what happened. The turns are touching each other. We have a partial short. Look what happens to the ohms value, drops significantly. Very important when you are checking out the electrical solenoid on the 4-way reversing valve that you get the proper ohm rating. If you do not get the proper ohm OHM reading, that solenoid usually is field replaceable without taking out the whole 4-way valve. That's an easy part to change out. Okay, here we have the 4-way valve. This shows the position when the solenoid is de-energized here. So be aware when you see this in the de-energized, this is probably going to be in the heating mode. Notice that we have pilot ports here. And remember, I had a situation where this pilot line basically developed a leak. I was lucky. I was able to fix this thing out in the field for a customer in Temecula. And to my knowledge, it's working great at this point. Okay, now with the solenoid still de-energized, notice that the flow of refrigerant, we're actually taking hot gas from the compressor. We are now going through the de-energized coil, and basically the refrigerant is blocked from going this way. So we are now going to the indoor coil and we're causing heat to take place. Okay, in this particular case, now we have a different situation. The solenoid is energized, so that means we're now in the air conditioning mode. So we're taking hot gas from the compressor. Notice that it goes through the solenoid and basically it goes here to the outdoor coil. That means the outdoor unit is rejecting the heat that was pulled from the indoor coil. So we have refrigerant vapor going to the compressor. And then of course, from the indoor coil, we have the refrigerant, low pressure, low temperature, somewhat superheated vapor entering the compressor down here. Okay, here we have a where the bulb, okay, this is something we haven't really talked about. Let me find the illustration in the book, make sure that we get the correct information regarding this. Okay, this is going to be found on, let's see, this is going to be found on page 1282. This is under figure 43.17. This illustration shows that care must be taken in the choice of a TXV. If an ordinary TXV sensing bulb were to be mounted on this gas line, it would get hot enough to rupture the valve diaphragm. So be careful where the TXV sensing bulb goes. The manufacturer will tell you where it goes. Don't put it in the wrong position. Otherwise, you could actually rupture the power head here. Not a good idea. Now notice here that closed check valve forces the refrigerant to flow through the TXV during cooling. And this figure is going to be found under same page 1282. In this particular situation here, the check valve forces that refrigerant to flow through the TXV and no problem. So here's a check valve, and basically what's happening is the refrigerant is flowing through the TXV and blocking the bypass because there's a check valve here. In this position here in the heating mode, basically a check valve opens to allow high pressure refrigerant to bypass the TXV. So in this particular place here, the refrigerant vapor goes through here through the indoor coil in the heating mode. And notice what happens is this TXV is bypassed. It's blocked and it's allowing refrigerant to go directly out. So you have a check valve for the TXV or for the metering device to prevent the metering device being used. Remember, you have two metering devices, one for the indoor section, one for the outdoor section. Depending on the direction of flow of refrigerant will determine if you're blocked or open. Okay, in this case here, it shows electric heating elements of the air handler, return air. Here we have the refrigerant vapor liquid on the evaporator coil and the A coil above here. Now, what's wrong with this picture? What is wrong with that picture? Okay, look where the heating elements are located. The heating elements should never, never, never be installed below the evaporator coil. Okay, in this case here, this heating element needs to be installed above. When I installed this heat pump project in Port Orchard, Washington this summer, the evaporator coil was located down here, and a strip heat package was located up here along with the fan, which is fine because it was a downflow application. So notice that the correct installation shows the electric strip heat elements be above the evaporator coil, or the indoor coil in this case. Okay, this shows the winter heating cycle utilizing R410A. Look at the pressure temperatures. We talked about this morning in the PowerPoint. Notice I got 35-degree temperature going here. I'll bet you this coil is already starting to frost up by looking at this illustration. Suction pressure of 51 psig corresponds to a refrigerant boiling point of 2 degrees Fahrenheit for R410A. And notice that in this case here, this is acting as our extractor for heat to the outside air. And of course, that heat is being brought in and sent up through the ductwork. Remember, when these heat pumps are operating correctly, they're charged correctly, typically we're going to get a supply temperature of close to 100 degrees. Okay, here's an illustration showing how we can measure the temperature of the of this four-way valve. This is a good piece of information to know because a lot of people have asked me in the past, how do you troubleshoot a four-way valve? Well, the best way I know how is to take temperatures. And this illustration, which I want to call your attention to, I believe it's in your textbook. Bear with me while I find it for you. Is a good indicator of this valve could be having a problem or not. So this is going to be found on page 1308 of your textbook under figure 43.56. The method for checking performance of a four-way valve using the temperature comparison. So basically, you're looking at the temperature comparison right here. Okay, if we have more than 3 degrees, much as I hate to tell you this, we got a leaking valve. We don't like that. So basically, in this situation here, let's take a look at this first illustration. From the outdoor coil, we got 30 degrees going in here, 40 degrees coming out here. And why is that? Because we're leaking internally right here. Now, in this situation right here, we have the same situation. We have 50 degrees going in here. Notice that we have some refrigerant leaking in here, and same scenario. So in the cooling mode, we're showing a decrease in performance of the indoor coil because we have an internal leak to the reversing valve. The only way you're going to find this out, folks, is you got to do temperature comparison checks. That's the only way you're going to find out. Okay. Now, one thing I have not called your attention to, and this diagram makes it very, the center port is always called the permanent suction line. The middle port on the other side of the four-way valve is the permanent discharge line. Okay, the air pressure switch is going to detect blockage of airflow through the outdoor coil. And don't forget, the timer is designed to close every 10 seconds of 90 minutes of operation. And if this outdoor stat is not closed, basically we will not go into defrost. In this case here, we have an air pressure switch to sense ice buildup. So what happens is when this switch closes, because the outdoor coil is icing up, this will close. Obviously, the temperature will drop. And once it reaches the 90 minutes and the 10-second drops, if these two switches are closed, we go into defrost. It's as simple as that. And last but not least, here we have outdoor unit with heat pump coils. This is a chart. One of the things when you install heat pumps, there are so many different variations out there. We cannot call your attention to just one heat pump. Manufacturers have specific specifications. They're going to show you what the BTU ratings are depending on the coil combinations. This particular chart here, see if I can find that for you. see if it's in the textbook. This is found on page 1288, figure 43.26. These are the rating tables for air-to-air heat pumps. And this is courtesy of Train. Notice they give you the model numbers, they give you the type of metering devices, they give you the SEER ratings. EER is the one you want to pay your attention to there. That's the number, is basically tell you how much it's going to cost to operate here. And notice that these model numbers change depending on the size of the equipment. Outdoor unit. The one thing you want to make sure when you are installing this equipment here, more than anything else, you need to make sure that you have the right indoor coil match to the outdoor section. That's just don't just rely on the guy behind the desk. He may or may not understand all this stuff. You need to look it up to see what the limitations are. You also need to do a heat loss and the heat gains calculations of the structure where you're putting in a heat pump. If you don't do this, you're going to come up short. It is as simple as that. And with that, that's the end of my presentation on air-to-air heat pumps. Thank you for listening.